So our last topic in this chapter is buffers, and buffers are solutions that resist changes in pH. So solutions that resist, okay, I feel like the Borg here, changes in pH when small amounts of acid or base are added. So when small, okay, so large amounts, nothing's going to resist. Amounts of acids or bases are added. So resist, I'll put that in scare quotes because there's really only so much the buffers can do. So your blood is buffered, but quite frankly, if you inject yourself with hydrochloric acid, you're probably going to kill yourself, even though it's buffered. If you inject yourself with a large amount of a strong acid, there's nothing that's going to be able to resist that. So it can only work up to a point. It turns out that buffers are kind of interesting because they always contain two components. So there's two things present in solution to be a buffer. And the first thing is you need a weak acid. And the second thing is need the conjugate base. So if you remember from Bronsted-Lowry theory from last week, the weak acid, right, is the one that's got the extra proton, and the weak base is the one that's got the one fewer proton. So if you remember, it's a game of catch. So we play catch the proton lightsaber, right? The acid has the proton, and as it throws it away, right, it becomes the base because it's lost it. And then when it catches it again, right, it's reforming the acid. So our classic weak acid, of course, is acetic acid. So HC2H3O2. This is acetic acid, and of course it can react with water, and it can throw the proton. So acetic acid can go ahead and throw the proton at water, and when it throws the proton at water, it forms the conjugate base. So what we've done is we've removed the hydrogen, but of course the hydrogen, let's get rid of that lightsaber. That hydrogen, right, has a positive charge. So if it takes away a positive charge, it leaves behind a negative charge. So that is the acetate ion. And of course it gave a proton to water. So water's, instead of H2, it's H3O plus. Okay, and remember that game of catch can go back. The water can throw, or the hydronium ion now can throw the proton back, and it can reform the pair. So we've got our conjugate acid-base pair. So in blue, this is my one. So this is my acid, and this is the form with one fewer proton. That's the base. And if we cared about it, right, the water here is acting like the base because it's picking up a proton, and over here the hydronium ion is acting like an acid because it's donating a proton. So if you wanted to identify the second conjugate acid-base pair, it would be this one right here, and again you are adding a proton and you are throwing a proton, so the acid base. So there's my acetic acid in the acid form. It's a weak acid, which means that it doesn't 100% break down, and there's my acetate ion, that's my conjugate base here. And so taken together, if I had a solution that had both of these, it would make a buffer. So you might say, well, that's pretty easy, right? So to make an acetate buffer, I need my acid and I need my conjugate base. So all I got to do is get both of these present. And if you go into the stockroom, you can actually find acetic acid. We can buy acetic acid. But if you go in your stockroom and you look for the second thing, you cannot find it. And the reason you cannot find it is that it doesn't actually exist by itself. And the reason it doesn't exist by itself is that it's only half an ionic compound. It's the same way you can't have your left-hand side of your body go to campus and take class and let your right-hand side of your body stay home and sleep in bed. They always come together. Now, they might dissolve in water and fall apart, but you always get both things in water, so you can't have one without the other. So we need what is called the counter ion, and so we need the other part of it. And if this is a negative ion, then we have to have it a counter ion with the opposite charge to counteract it. And my favorite counter ion is sodium. Sodium, it turns out to be a very boring neutral ion. And so if we actually went ahead and looked in our stockroom for acetate, we couldn't find it, but we could find sodium acetate. And sodium acetate is also the thing we sprinkle on potato chips, and when it reacts with the slobber on our tongue, and it forms acetic acid. So salt and vinegar chips, which are definitely the best flavored chips in the world, they contain sodium acetate. That's that white powdery stuff on there that makes it taste like vinegar. So we could make an acetate buffer by taking both acetic acid, and the acetate ion in the form of sodium acetate, and that would make a buffer. There's various other buffers as well. So for instance, we can take ammonia and ammonium, maybe in the form again of something like ammonium chloride. So we need a counter ion, so chloride works pretty well. And ammonia is a weak acid, ammonium is a weak base. And another way to look at it is a buffer is also a base and its conjugate acid. So it's exactly the same thing looked from the other perspective. And again, it needs to be a weak base and a strong, and a conjugate acid, I suppose. So the thing that got me, and I taught this class for many, many years, and I thought, well, I hope no one ever asks me this question. So if you've got a buffer and you need a weak acid and its conjugate base, I always thought, well, I hope no one ever asks me this, is why don't they react with each other? If this is the acid and this is the base, and normally acids and base react and make a salt and water, so why don't they neutralize each other? So I really, really hope no one would ever ask me this question. And actually, many, many years ago, I was driving a little metro, and it was probably July. We were under quarters, and I was teaching the class. As I got to the top of the hill, which was really a struggle, it suddenly came to me in a flash of green lightsaber lightning. And here's why they don't neutralize each other, or if you prefer, here's why they do neutralize each other, but it doesn't matter. So the weak acid and the conjugate base are actually always neutralizing each other, but it doesn't matter. And if that seems like I've just said something crazy, this is why. My acetic acid, if it loses the proton, it forms acetate. And if the acetate has gained the proton, it forms acetic acid. So they've neutralized each other. Okay, we've just played a game of catch the proton. So the proton, let's go with a red proton here, is gone from the acid to the base and neutralized. But of course, what has it formed? Well, the acetic acid has formed acetate, and the acetate has formed acetic acid. And if you ask yourself before and after, you start with acetic acid and acetate, and after you end up with acetate and acetic acid. So of course, they both neutralize each other all the time, but they end up reforming each other. So that's why buffers don't cancel each other out. And you might be asking yourself, well, why do you need both the acid and the base? And of course, the acid and the base are both needed because the weak acid, its job is to neutralize added bases. So the acids can neutralize an added base. And if you've got the base in your buffer, the base is going to neutralize any added acids. So you've got two things that are capable of neutralizing their opposite numbers. And of course, they can neutralize it themselves, but they just end up making themselves again. So if you had ammonia, ammonium chloride, the ammonia is the base. It can neutralize any added acids. The ammonium is the acid form. It can neutralize any added bases. So buffers have to have both the weak acid and the conjugate base, or the weak base and the conjugate acid, and the acid neutralizes bases and the base neutralizes acids. And the reason they don't neutralize each other is because they do, but they end up just making each other. So let's look at a biological buffer. So the carbonic acid bicarbonate buffer is a biological buffer, and this actually controls the pH of your blood. It's coupled to the respiratory system. Carbonic acid, we haven't met before in this course, but it has a formula H2CO3, and the bicarbonate buffer, well, it turns out when carbonic acid reacts with water, then it forms hydronium, and it forms bicarbonate. And again, when you've got both these in solution, so you've got the weak acid and you've got the conjugate base, then you've got yourself a buffer situation. So if any bases interact with your blood, then they're neutralized by the carbonic acid in the blood. And if any acids are introduced into your blood, maybe from exercising and working out, all those acidic compounds enter your blood, they're neutralized by the bicarbonate ion in your blood. And actually, most of the time, you have to worry about acidic things entering your blood. So your carbonic acid bicarbonate buffer actually has a lot more bicarbonate in it than it does carbonic acid. One interesting thing is actually these is all coupled together. So if you wonder where this comes from, the water and the carbon dioxide from the air you breathe in, they can combine and they can form carbonic acid. And the carbonic acid can go ahead and react and form H plus and the bicarbonate ion HCO3 minus. So you've got this very nice equilibrium here, and they're coupled together, so your lungs are where water and CO2 come in and come out, and your blood is where your carbonic acid and your bicarbonate are present and are found. So you've got these two systems coupling together. And we'll just talk about one little last thing, and then I think we'll actually call this course a day. And you might remember, of course, hyperventilation. You might know that if you breathe excessively, this is a bad thing. And why is this a bad thing? Well, if you breathe out an awful lot, then you lower the concentration of CO2. And if you lower the concentration of CO2 because you've got an equilibrium, we know there's a Le Chatelier shift. And so if this is the stress, the relief then is to shift to the left to make more CO2. And so you can shift to the left to make more CO2. And so that reestablishes equilibrium. And of course, if you're shifting to the left, then you're basically taking carbonic acid and you're breaking it down and you're replacing the CO2. So if there's less carbonic acid, so if there's less of the acid, then that means your pH is rising. And so this is called respiratory alkalosis. If I can spell respiratory, is that right? I'm not sure. You'll have to fix that in your notes. Alkalosis. And so alkalosis means that alkaline, so high pH is alkaline. And how do you normally fix this? Well, one problem with removing CO2, right, is that it causes the breakdown of carbonic acid. But if you breathe into a paper bag, you can breathe back in the CO2. And so if you're increasing the CO2 concentration, you can shift things back to the right to reestablish equilibrium.